reason I like giving you a worksheet is because that's like what your test is going to be. So that's the reason I want to give you this worksheet instead of having this due. Okay? So it's, right? Oh, and this thing about the playing along, okay, basically I'm going to take this, and you know how I use a stylus to write on this and it shows up here? What I've done in the past is to kind of work through drawing 4 Lewis structures, just me, and by the end of the 4 Lewis structures I was like, yeah, I got it. So instead of doing that, I'm going to pass this along, and you guys are going to do your Lewis structures kind of step by step. Okay? All right. Yeah. But in the meantime, I kind of want to revisit this idea of resonance structures, because resonance structures, and we're going to bring in the formate Lewis structure here in a minute. Remember, that was a carbon, single bond, single bond. Okay, this is what I call the preliminary Lewis structure. Okay, you know it's preliminary, and I alluded to a step number 5. What's wrong with this structure? What's carbon got going on?
Carbon doesn't have a full octet.
Yeah, carbon doesn't have a full octet, exactly. And actually here, what we did yesterday is we swung, I think it might have been actually these, but we swung a pair of electrons in and made it a pi bond, okay? And then carbon could get its complete octet, and oxygen keeps control. It's like a joint custody sort of thing. But the thing is, I could do it there, or I could do it here, okay? If we call that atom oxygen atom A and that oxygen atom B, and those are what we call resonance structures, okay? So this talks about actually, and this makes sense, the delocalization. So if something's delocalized, it means it doesn't have a home, basically, right? So here's the deal. For instance, if we look at, you guys would tell me that pink and purple is a pi cloud, right? A pair of electrons. They're like delocalized, right? Okay. So actually, if we were to swing from carbon A, okay, like we did before, that's kind of this scenario. Carbon B, or excuse me, oxygen A, swing a pair of electrons. That's this scenario. Swinging from oxygen B, that's this scenario. So kind of in between, basically what the formate ion does is probably kind of go back and forth between those two, okay, in reality. So here they are, kind of A and B, swinging the lone pair electrons from the north and then from the east. Okay, so what really happens is probably somewhere in between, like this. Okay, in chemistry, actually in Unit 4 in here, we're finally going to talk about chemical reactions, where you kind of read them from left to right. You start with probably reactants you're familiar with, and you end with products. But honestly, there's a lot of things in chemistry that actually go back and forth. And instead of a one-way arrow, we show a two-way arrow. Okay, so that's kind of a back and forth sort of thing. So in the case of the formate ion, whether you swing from the A oxygen or the B oxygen, or the north oxygen or the east oxygen, they are both equally cool. Okay, they both make sense. Okay. But I'm going to show you an example of a pair of resonance structures that one totally doesn't make sense. So not all possible resonance structures are contributors. Okay. So this is kind of talking about the rhino, kind of between the two mythical creatures. So when I show you the example, and it's carbon dioxide here in a minute, where we're going to swing the lone pair electrons to make a pi bond, these are things that you look for. Does it make sense? So first off, you know, does swinging give you complete octets? Well, that's important. Okay. Let's see, there must be another one here. Yeah. This is the one that actually, for one of your structures, you're going to have to figure out how to swing, okay, because of the expected valence of an atom. Just to kind of remind you, we talked about expected valence of an atom. The expected valence of an atom is 8 minus the group number. Okay, so for instance, the halogens are group number 7. Okay, so group 7A, the expected valence is 8 minus 7, or 1. Okay, 6A, it's 2. Okay, etc., etc. 5A, it's 3. Okay, so in a neutral molecule, okay, you expect an element in that particular column to reach out that many times. Remember, here we're talking about sigma and pi bonds. We kind of switch it up. Hybridization, of course, is sigma lone pair electrons. So this is a little different. So here we go, carbon dioxide, the last thing I want to cover about this. So carbon dioxide, let's see, we're going to actually go to the periodic table. Carbon has, what, 4 valence electrons. Each oxygen atom has 6 valence electrons, so 6 times 2 is 12, plus 4 is 16. So we should have 16 electrons distributed around our final Lewis structure. Okay, and both of these have 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons. Okay, and if I call this A and I call this B, how many people think A looks better? Me too. Most students do. They're like, yeah. Okay, why does A look better?
More balance.
More balance, exactly. The other thing about A is we said that oxygen is a 6A element, and the expected valence of oxygen, we can take 8 minus its group number, so what's its expected valence? If it's 6A, 8 minus 6 is? So actually, and this again, this is what you're going to use for one of your structures today. Actually, its expected valence is 2. And that, by the way, again, that's just the 2, the sigma and the pi bonds. So can you see it's reaching out twice here? Okay, whereas oxygen here is reaching out once, and here, this oxygen is reaching out 3 times. Okay, it's not following the expected valence rules. Okay, so yeah, that's it. And so basically, you were right. That one doesn't contribute any. And don't worry about these either. Okay. And Robert's like, dang it, or turn them in for extra credit. I like to see that. Okay, let me know if you have any questions about the extra credit. Extra credit will be due on Monday, though. Okay, so now